Hey everyone, today we will be focusing on depth first search for a balanced tree, and without any further hesitation, let's get started. And now focusing on depth first search. So depth first search, as the name suggests, or states, focuses on traversing and searching through a tree within the depth mode. So we're going to start with our root, but then we're actually going to go from leftmost depth all the way back to the rightmost, sort of like a giant circle per se. So depth first search would go to the leftmost and then goes to the right, outputting the following. So I also did a test beforehand just to be able to clarify. So if we have a following tree right here, if we have 20, 10, 30, there's like this giant circle that it's already going through from the leftmost, and it'll also go to the other subtrees as well, to the right. And depth first search is will be considered in that case. So breadth first search versus depth first search. There are key distinctions between the two. So breadth first search, we can imagine little circles right here going through each level, but depth first search is a giant circle going to the leftmost all the way to the rightmost. And so the way we're actually going to construct depth first search, another key distinction, is that breadth first searches also use queues, but depth first search use a stack to keep track of everything. And as we know before from our previous videos, that stacks are can be considered a stack of plates where it's last in, first out, and that's just a general principle to keep in mind. So the first thing we're going to do, we're going to include the library of stacks. It's called include stack, so we have to call that from the STL library. And so we're going to be focusing on depth first search by doing void DFS, and then I'm going to take the root as a parameter, so node root. Then if we're not at the root, we will just return just to initialize, and then we're going to initialize our stack with stack node for S, and then we're going to push our stack with the root as a parameter, so we go through continuously, and while stack is not empty, we'll have node equal s.top, indicating that we're going to have the node at its given top, and we're going to output the following data by doing count node key, indicating the actual data of the specific node, and put it in the list accordingly. Then we're going to pop the stack so we can go through at each component of data. And if the node is particularly at the right, we will push the information of the stack on the right hand side, and the order is very critical, so that way we actually can replicate the nature of it. So right here, node left, but beforehand depth first search started from the left then to the right, where in this case within our function we have right and left accordingly, just to push everything already set in place. So going to go down, depth first search, similar to breadth first search functionality, depth first search of the balanced tree, depth first search, ABL root. Let's just run this bad boy, see if it goes through. And yes, it does. It does go through. So we have the following tree that we have, then we have the following outputs, 10, 20, 10, and 30. It goes through in a big circle, and we have similar outputs because of the size of our tree, namely. So we have 3 points. So just for general context, depth first search uses stacks, breadth first search uses queues, and depth first search can be thought of as like a big circle that starts from the root and goes all the way down and all around. And breadth first search can be tiny circles where we start from the root and go from the leftmost to the rightmost. So just a few things to be able to describe and communicate on. Now let's head over to unbalanced trees. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.